Let me give you one example. Let's take q of square root of 2 and square root of 3. Then, of course, the sum of those two guys is an example of a primitive element. Because this is an extension of degree 4, so q of square root of 2 and square root of 3, the degree of this over q is 4. So all sub-extensions are quadratic. And the element square root of 2 plus square root of 3 is not quadratic. You cannot find a quadratic polynomial which has this for a root, as no quadratic polynomial has square root of 2 plus square root of 3 for a root. This must be a primitive element. Generates our E. It is not contained in any proper subextension. So let me give you an example of an extension which cannot be generated by a single element. So take k, say, equal to fp, and consider k xy as an extension of k of x to the power p, y to the power p. Well, this is of degree equal to p squared. Now, if you have any alpha in kxy, of course, this is purely inseparable of degree p over k x to the power p, y to the power p, if it's not already there. So in the k of xy, but not in the k of x to the power p, y to the power p, is of degree p over k x to the power p, y to the power p. Since alpha to the power p belongs to this smaller field of pth powers. So no element like this can generate our extension. So now I would like to talk about normal extensions. A normal extension, by definition, is a splitting field of a family of polynomials. A normal extension of K is a splitting field of a family of polynomials in K of x. So we take a bunch of polynomials in K of x and we adjoin all their roots to K, and this is what is called a normal extension. For instance, a splitting field of one polynomial is also a normal extension. So theorem 3, the following conditions are equivalent for an extension L of K. First, for any x in L, the minimal polynomial splits in L. Second, L is normal, splitting field of a family of polynomials. Third, all homomorphisms from L to K bar have the same image and fourth, the group of automorphisms of L over K acts transitively on this set of homomorphisms from L to K bar. So let me prove this theorem. 1 implies 2. We just take Pi family of minimal polynomials of all elements of L. Then L is a splitting field of this family. Two implies 3. If we are a splitting field, then all homomorphisms have the same image. So if S is the set of roots of Pi in L, and S prime is the set of roots of Pi in K bar, then any homomorphism must send S to S prime. But S generates L. Over K. So phi of S determines phi of L. 3 implies 4. If I have two homomorphisms, if J and J prime belong to the set of homomorphisms from L to K bar, then they send L isomorphically to its image. So these are isomorphisms from L to its image L prime. So I can produce the following thing. So this is G prime and this is G minus 1. So I take G minus 1 times G prime. This is an automorphism of L over K and since J to J prime. Finally, 4 implies 1. I have this transitive action and I have to prove that any minimal polynomial splits. So consider the minimal polynomial of x in K. Let alpha 1 and so on, alpha n, be roots in K bar. Then I have a map sending Kx to K alpha I. Such a thing extends to J from L to K bar and sends x to alpha I. Now, well, I better denote it not J but Ji. Now, this is by the theorem on extensions of homomorphisms. And now I have theta I, automorphisms of L over K such that J1 times theta I is Ji. So alpha I must be lying in J1 of L. So all roots are in J1 of L, and the polynomial splits over J1 of L, but this means that it splits over L.